Hello everyone, welcome to this series of lectures on the course Calculus and Numerical Methods. This is part 3 of the Numerical Methods section, and in this lecture I will discuss the Newton-Raphson method to find the approximate root of a given function. Like the previous two methods, that is the bisection method and the regular falsi method, this method will also give us the approximate root. And we can find the approximate root as per the accuracy level that we need. All right. So let's see what is this Newton-Raphson method. Supposing I have a function with me from some subset A of R to R, which is differentiable. Okay, so its derivative exists at each point in the domain, that is A. All right. Now, supposing A and B are 2 points in A, such that f of A into f of B is negative. So they are of opposite signs, and therefore it is guaranteed that between this small a and small b, the function f will definitely have a root, right? So we will assume that f of a is negative and f of b is positive. Let's fix that f of a is negative and f of b is positive. All right. So let me draw this function in the xy plane, just a rough sketch. Supposing this is a x-axis and this is a y-axis, and supposing point A lies somewhere here and point B lies somewhere here. So I'll have a function. This is just a rough figure. Let's say somewhat like this. Then this point is here. I'll have f of a. So this point is a comma f of a, and this point is f of b approximately here. So this point is b comma f of b, right? So what I'll do is first I will check. I'll compute f of a and f of b, and I will check which one of them is closer to 0. Okay, so f of a will be something and f of b also will be something. We will see which of these are 0. Supposing f of a is close to 0, let's say, then I will take the first approximate root x naught as the point a. I've assumed that f of a is closer to 0. Okay, so you can just compare these two values and you can check which one is more closer to 0. That point you can take as the point x naught, right? So a is my x naught here. Although b looks closer in the diagram, I'm just assuming that f of a is closer to the root. Okay. Then at the point a comma f of a, I will draw a tangent. At this point, I will draw a tangent to this function. Okay, so I think I should draw a better function so that it's easy for you all to understand. I'll just remove this function and I'll draw a nice curve. Let's say I have something like this so that it's easier for me to draw the tangent. So at this point, I will draw a tangent. Okay, my diagram is not perfect. Let's say this is the tangent, more or less. Okay, supposing this is the tangent at this point. Now, this tangent will go and cut the x-axis at some point, right? So it is cutting the point here, the x-axis here. I will call this is the point x1. Okay, and what is tangent to a curve at a point? I have this tangent now. I will take the slope of that, and slope of that tangent is nothing but the derivative of the function at that point, right? So slope of the line segment joining x1 and a is, the y coordinate is 0 here, right? So that's f of a, that is x naught minus 0 upon a minus x1, but a is nothing but x naught, so that is x naught minus x1, and this is slope is nothing but the derivative of the function at that point, at the point a, which is nothing but x naught. Okay, so finally I have this expression with me. Slope is nothing but the derivative of the function at that point, and slope is also given by this expression, right? y2 minus y1 upon x2 minus x1. Using that formula, I can write the slope as this. So f of x naught will be equal to, I can just cross multiply this here, and I will bring f dash of x naught down, and this will be equal to x naught minus x1, and from this, if I transfer x1 on that side and this expression on this, on my right hand side, x1 will be nothing but x naught minus f of x naught upon f dash at x naught. Now this x1 which we obtained is closer to the root. The root is here, where I am marking in red, is closer to the root compared to the point x naught. So this x1 that we obtained is the first approximation. Sorry, the second approximation. The first one was definitely x naught. So this is the second approximation that we obtained, right? So similarly, what I'll do now, from here, I will mark the point f of x1, that will be somewhere here, and this point will be x1 comma f of x1. Okay, x coordinate and the y coordinate here. At this point, again, I will draw a tangent to the function, approximately. No, my line is not proper. So at this point, I have to draw a tangent. So let's say it is this. Then it will again go and cut the x-axis at some point, and I will get x2, right? So using the same idea now, what you can do is you can try to compute x2, and that will turn out to be x1 minus f of x1 upon f dash at the point x1, right? Following the same procedure as we did here to find the slope and equate it to the derivative. In simplifying, we obtain x2 to be x1 minus f of x1 upon f dash at x1. Okay, so x2 is the third approximate root that we got. So continuing in this manner, in general, I can write the n plus 1th approximate root as nth approximate root minus value of the function at the nth root upon the derivative of the function at the nth root. So using this expression, I can find as many approximate roots that I wish to. Okay, and up to the desired accuracy level, I can keep on doing until I get the required approximate root. All right, so this way of finding the approximate root is called Newton-Raphson method, or sometimes also referred to as RN method. Okay, so the first step here is to verify. This is the method that we will follow while solving the problems. So first, identify the points A and B. They will be given to you. In some cases, some people also give you the first approximate root x naught. Okay, and that time you don't have to check that, you don't have to worry about this A and B business. So that won't be required. If someone is giving you the first approximation x naught, then you can directly put that here in the last expression and you can find the first approximate root, that's x1. Okay, and using x1 you can find x2, and using x2 you can find x3, and you can keep on going until you reach the desired accuracy level. Okay, so first I have to find appropriate x naught. Okay, so choose appropriate x naught. That is the first approximate root. If a and b, if a range is given to you, a comma b, interval, then you compute f of a and you compute f of b, and whichever is closer to the root, you pick that a or b as x naught. Okay, so after computing x naught, you can use expression, I can put star here, you can use star to find x1. Okay, so x1 will be the first approximate root, and then you can repeat this process to get approximate root as per the desired accuracy level. Okay, so this is how you find the approximate roots of a function using Newton-Raphson method. One thing that is important here is the function must be differentiable at all the points in the domain that you are picking up here. Okay, otherwise this method cannot be used, because the expression to find the approximate roots, it involves derivative of the function at those points. Okay, so now I will look at a problem and we will find the approximate root of that using Newton-Raphson method. This problem says find the root of the function f of x is equal to x cube plus x square plus 3x plus 4 in the interval -2 comma -1, correct up to 2 decimal places using Newton-Raphson method. And the table that we are going to use for this method is this. So this is the first column that will give us the number of iteration. This is the nth approximate root at each stage, the second column. The third column will compute the next approximate root. I will tell you all how I got this expression. I have written the simplified expression here. And then the last column will give us the difference between the approximate roots at each stage. Okay, so I have the function here. I will compute its derivative and keep first. So that's 3x square plus 2x plus 3. Okay, so this is the derivative of this function. Now we will compute the value of the function at the point -2 and -1. So if you look at the value of the function at the point -2, that will be -2 the whole cube plus 3 times -2, sorry, -2 the whole square plus 3 times -2 plus 4. Okay, and you can easily check that it turns out to be -6. Okay, so and that's negative. Then I look at f of -1. This will be -1 the whole cube plus -1 the whole square plus 3 into -1 plus 4, and that turns out to be +1. Okay, which is a positive number. So definitely there is a root between -2 and -1 for this function, right? Then to start with the first approximate root, you pick up that value either a or b whose value such that value of the function at that point is closer to 0. And from here it's clear that 1 is closer to 0 compared to -6. So I will choose the first approximate root as x naught, and that will be -1, because value of the function at the point -1 is closer to 0 compared to the point -6, right? So the 0th iteration, or you can say that it's the first iteration. In fact, you can start with x1 also here, because that these are just notations. Okay, so x0 would be -1 here. Now xn plus 1 is given by the formula xn minus value of the function at the point xn upon derivative of the function at the point xn, right? So in this expression, I will drop the value of the function at the point xn. F of x is this, so f of xn will be xn the whole cube. You put x equal to xn in the function here. Okay, so that is xn cube plus xn square plus 3 times xn plus 4, right? I can write it here, plus 4 whole thing divided, no, not whole thing, this part divided by f dash at xn. So in f dash you put x equal to xn, that will be 3xn square plus 2xn plus 3, right? And now I can simplify this. You cross multiply here and you simplify the terms in the numerator, and you will see that the first term gives 3xn square into xn, so that will be 3xn square. 2xn into xn, that will be 2xn square. No, I have to subtract 1 xn cube from here, so this is not 3, this will be 2, right? Because this will be 3xn cube minus 1 xn cube is there, so that will be 2xn cube. Then 2xn into xn will be 2xn square minus xn square, so that is going to be 1 xn square, so that's xn square. 3 into xn will be 3xn minus 3xn I have inside, so they will cancel out and I won't get anything there, right? And minus 4 I will have here, so that's minus 4 upon this term in the denominator, so that's 3xn square plus 2xn plus 3. So you can simplify this first only, the formula for xn plus 1, right? And you can put that directly here, the simplified expression. Otherwise at each stage you'll have to do all this computations to find each xn plus 1. So you compute that first only and you keep it ready, and you then just put the values of xn's here to get the xn plus 1. Okay, now if you put this is my xn right now, so to get x1, this is x0. To get x1, I will put x0 is equal to -1 here. Okay, so this will be 2 into -1 the whole cube plus -1 the whole square minus 4 upon 3xn 3 minus 1 the whole square plus 2 into -1 plus 3. Okay, so I will just compute one and I will show you all. So x1 will be 2 times x0 cube plus x0 square minus 4 upon 3x0 square plus 2x0 plus 3, right? And x0 is -1, so I will put -1 here. So this will be 2 into -1 the whole cube plus -1 the whole square minus 4 by 3 times -1 the whole square plus 2 times -1, and that's plus 3. Okay, so if you put this on your calculator, you will see that this expression turns out to be minus 1.25. Okay, it's very simple computation. So that's minus 1.25. So this value of x1 I will take and I will put it here, minus 1.25, right? So this is the second approximate root denoted by x1. Okay, or you can call the first one x0 is the 0th one and this one is the first one. Now in this case we can directly compute xn plus 1, that is x1 minus xn, and that is x0, right? So x1 minus x0 and its absolute value, you will see that it turns out to be 0.25. Okay, so this minus this x1 minus x0 and then you take the modulus, it will turn out to be minus 0.25. So minus will disappear when you take the modulus. right? Now my x1 I will take and I will get it here. So this point will be minus 1.25, and now I am ready to compute the point x2. This is the first iteration, right? So the way we computed x1, you can compute x2, right? So x2 will be what? x2 will be, you put the value of x1 here. So that is 2 times x1 cube plus x1 square minus 4 by 3 times x1 square plus 2 times x1 plus 3. Okay, and then you put x1 is equal to minus 1.25. Wherever you can see x1, you can drop that value, and you can see that this value of x2 here, it turns out to be minus 1.22289175. Okay, a simple calculation, you put x1 equal to minus 1.25 here, and you will see that you are getting this answer, and that is the third approximate root, that is x2. Then you can compute x2 minus x1 absolute value of that. Okay, and this difference at this stage will turn out to be 0.0271, right? So I will erase this rough work which I have done here. So we have got the third approximate root. Now we are ready to compute the next one. We have to go on computing this until we get the desired error level. Okay. So the next iteration will be, you take this value of x2 and you get it here, minus 1.22289157. Okay. And similarly, now you can compute the value of x3, that is the fourth approximate root. Okay, it shouldn't be difficult. So this will turn out to be minus 1.2224946. Okay, and this difference x3 minus x2 here, so that is x3 minus x2, and the absolute value you take, and that will give you 0.000396. Okay, and the error level has already gone below the desired level. We wanted 2 decimal places, that is 0.001, this error level, right? And it has already passed that, so we have obtained the approximate root up to 2 decimal places, accurate up to 2 decimal places. Okay, and that's this x3, and therefore the approximate root correct up to 2 decimal places is this value, that is minus 1.2224946. Okay, and this is the approximate root of the given function using Newton-Raphson method. All right. So these are some problems for you all to try. Find the approximate root of this function in the interval 2, 3, correct up to 3 decimal places using Newton-Raphson method. And one more function is given, cos x minus x times e raised to x in the interval 2, 4, correct up to 2 decimal places using the Newton-Raphson method. All right. So I will end this video with this. I hope you have followed this. You can solve these answers and keep them ready. Okay.